or this probably this sand particles, right? They may be kind of attached to those particles, and that will be give you a misrepresentation. So what is the way out? The point is that we need to remove those fine particles. How will be removing those fine particles, which is being said as a like sticky particles, right? So the sticky particles which are of fine grained, right? Fine grained means they will be less than 75 micron, right? So we need to wash it out. How will we be washing it out? By using water, and distilled water is actually preferable, right? For not having any kind of chemical influence, right? So that's how we actually be performing this sieve analysis for the particles which are above 75 micron. So what to do with the particles below 75 micron? So obviously sieve is not kind of permissible, as I was mentioning, that's because this particle will kind of flock together, and it will give you a misrepresentation. So the way out is the sedimentation analysis, right? So now sedimentation analysis requires this particular law, the Stokes law. Hello? 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 Am I audible?
Yes, sir. Yes, sir. You are audible.
Yeah. Okay, so for this particles which are less than 75 micron, we'll be performing this sedimentation analysis. Now, what is the logic behind this sedimentation analysis? We actually consider that a particle will start to settle, or means we know that any material in this nature will kind of try to attain an equilibrium state, right? So that's the kind of objective of all the material, right? And so for that, this particles also, right? So the objective is to reach to that equilibrium state, right? And what we have studied in our engineering mechanics class is that when a particle kind of flow on other substance, right? Or when a particle is there in any kind of material, any other foreign bodies, it is being kind of, there are few forces that kind of acted on that particular particle, right? Obviously weight is one of the force, right? Apart from that weight, you have this drag force as well as this buoyant force, right? Buoyant force will be because of that this Archimedes principle, and this drag force due to this Newtonian mechanics, right? Now equilibrium state is that when your weight force will be kind of equated this D and B, right? So the summation of the drag force and the buoyant force need to be equilibrated by the weight force. So that is the kind of objective of each of the particle, right? So particle will settle on this medium, and the medium that we'll be considering over here is water, right? So what we'll be doing is that we'll take certain amount of soil which passes through this 75 micron, and we'll put it, will kind of place it on water, right? Now the particle will start to settle. How long will the particle be settling? Till the moment it reach to this state, right? So this particular equation is being kind of attained, right? And if we just kind of use this drag force and this buoyant force, weight force, if we just write the expression of this forces, then eventually we'll be getting an equation where we can see this last equation where V is being denoted as velocity, which is kind of function of a constant number and the diameter of the particle, where capital D is actually referring to the diameter of the particle, right? So yeah, don't get kind of confused with this D and this D. Although I should have mentioned different things. So this is the drag force and this D is the diameter part, right? So once this equilibrium state is being attained, so your velocity, now this velocity is being actually being termed as like terminal velocity because of the fact that terminal velocity is treated to be a constant velocity, that once this particular velocity is being attained, the particle will kind of flow with that constant velocity. Before that, there is some kind of turbulence on the particle. So when this thing is being achieved, so there is a kind of laminar flow, right? So by using that sedimentation analysis theorem, what eventually we are getting is that V is a kind of function of your diameter alone, because this coefficient, this gamma S, gamma W, and eta, which is being which is actually your viscosity, or especially dynamic viscosity, these are kind of, you can take it to be a constant number, right? So if there is no change in the environment, obviously if there is increase in temperature, gamma W will be changing. If there is increasing or decreasing in temperature or pressure, this eta will also be changing, right? If I say all your environmental factors, and so for that matter any other influencing factors, remain to be constant, your terminal velocity will be proportional to this d square, right? So what does that mean? Higher this diameter, higher will be the terminal velocity, right? And that is the logic of using this particular theorem into account. And so that is your sedimentation analysis theorem, by using the Stokes law, wherein what we are doing is, we are kind of, our objective is to get this diameter of each individual particles and the percent finer, right? Because to, as I was mentioning, for drawing grain size distribution curve, we need two stuff, right? The diameter, and corresponding to that diameter, the percent finer, right? And so what we'll be doing over here, that we need to have this velocity, which is your, let's say, if I just take one individual particle, what you can see is that at a particular depth, right, you have this this is your HE, which is known to be effective depth. So this is something which is measurable. How will you be measuring it? You can measure it by using two different approach. One is known to be pipette method, the other is known to be hydrometer method, right? So hydrometer method, what it will provide to us, the hydrometer method will actually provide us this HE, right? So how this HE is actually going to vary with time, right? So if I know HE, and if I can get this HE for, let's say, the kind of for particular or for specific time, right? And this is a constant number, so I can get this D value, right? So that is actually the way we use this hydrometer method. So the objective is very clear. So in this, what we are doing is, we are taking the help of this sedimentation analysis, and especially the Stokes law, wherein we are actually in a process of determining this effective depth, which is this HE, right? And HE will be obtained through that hydrometer, right? If we perform hydrometer analysis, which will be obtained through that hydrometer. If we perform pipette method, which is normally not being performed in many of the laboratories, so therein also we'll be getting this HE part, right? So and through this equation, then we'll be getting this diameter part. Now the next thing which is remained is that percentage finer, right? So how will you be getting that percentage finer? We'll be seeing it, that how to perform this hydrometer analysis and how to get that percentage finer, right? So while performing this hydrometer analysis, we have to take some precautionary measures, right? One of the precautionary measure is because of the fact, as I was mentioning before, that the particles which are below 75 micron, right, they are these fine particles are charged particles. They will be flocked together and then they will settle together, right? Obviously, if they will flock together, diameter will be increasing, and higher the diameter, higher will be your velocity. The particle will start to kind of settle faster, and that will give you a misrepresentation, right? So we need to avoid that part. So what is the way out? So use some kind of chemical stuff so that the particle doesn't flocculate, and these are known to be deflocculating agent, right? And these are some kind of deflocculating agent that are being suggested in the course, so that we kind of add to the water before adding the sample as such, right? Now, so this is a jar which contains that this deflocculated this chemicals along with this 1 liter distilled water and with the sample as such, right? So that is need to be poured in this kind of another jar, which is where this measuring units are being provided, right? Because this is where we will actually perform the hydrometer analysis, right? Now it is being suggested that the entire amount of this this substance should be up to 1000 milliliter, right? So after pouring this sample on this measuring tube, if this sample is not like 1000 ml, if it is like 700 ml or 800 ml, right, we need to pour this distilled water, right? So upon pouring this distilled water, it will reach to the 1000 ml, and then we need to shake it, and we need to shake it vigorously to make the sample to be homogeneous, right? Once the sample is homogeneous, what it suggests is that everywhere number of particles or the arrangement of particles are in a sense same, right? Let's say if I just see these two layers, right? So all number of these big particles, if there are two big particles over here, in this particular layer also you'll be seeing two big particles. If there are middle shaped particles are, let's say, 6 in this particular layer, right? So that this middle shaped particle will be 6 over here as well, right? So after this, now when you give time for this material to settle, so what we have seen is that higher the diameter, higher will be the speed of settlement, right? So this terminal velocity of the particle will be quite higher, right? So this big particle will be settling faster than the small particles, right? So for the same layer, let's say after half an hour, what we can observe it, like for this layer, there are only two particles remaining, right? And over here, this you have the 6 particles, right? So what we need to see, we need to get this percentage finer. That is our job. How will be getting this percentage finer? So by seeing this, so let's say if you have to get the percentage finer of this region, yeah. Hello.
Casing Baghel, please unmute your microphone. Mr. Baghel. Casing Baghel.
यार ये वहाँ ज्वाइन हो रहा है, वो बोल रहा है बंद करने के लिए। कहाँ से बंद होगी?
बाघेल जी अपना माइक म्यूट कीजिए। Yeah, Dr. Manash, you can.
Okay, yeah. So the number of particles in each layer will be changing, and our job as an engineer is to understand that how many number of particles are being retained after a particular after a specific time, right? Now let's say if I have to refer to this particular layer which is not being marked by this green box, right? So how many number of particles, or what are the particles that are being retained, right? That need to be put in this particular equation. And what were the particles that were there before this settling actually started, right? So that need to be traced out, right? And this will give us the indicator of this percentage finer, right? Again, how will we be doing it in the laboratory? We'll be doing it again through that hydrometer part, right? So in that hydrometer part, what we'll be getting, eventually we'll be getting one particular number which is known to be hydrometer reading, right? So that hydrometer reading will be used for determining these two values, right? One is the diameter of the particle, right? And how will be getting this diameter of the particle? By from this equation, right? We have to get this He from that hydrometer reading. Now there is a kind of relation, and I am not covering that particular part right now, that how that hydrometer reading and this effective depth, they are being related. Now that is being available in code by this something known to be calibrating chart, right? So for each of this hydrometer reading, this He is fixed, right? So that you can get from that hydrometer reading. And then next, what you need to do, that the next objective is to get the percentage finer. How will you be getting it? Again, you have one data, hydrometer reading, right? Now that hydrometer reading need to be incorporated into, again, you have this one particular equation. So I suppose, yeah, no, it's not being mentioned. Again, so that particular equation will give you that percentage finer, right? So this slides actually are meant to show you this kind of will give you the glimpse of the importance of this hydrometer reading, right? So hydrometer reading will be used to get this He, right? He eventually will give you two values. One is this diameter and the other one is percentage finer, right? So we'll be getting this diameter by this kind of inverse approach, and we'll be getting this percentage finer by the direct approach, right? So once these two values are being obtained, then we need to get this grain size distribution curve, right? Now, obviously, is this method completely justified? No, obviously, because we have a lot of assumptions. Remember, this thing in soil mechanics are full of assumptions, right? It's completely empiricism, and lots of assumptions are being involved. But as an engineer, we need to be kind of aware of those assumptions, right? Because this is the method that is being suggested to us. But once the data is being given, we need to adjust something so that these limitations are being kind of, or this assumptions are being get rid of in some way, right? So obviously one stuff that I told you, that the Stokes law is based on this thing, that this particle, I was talking about particle diameter, right? And how we say about particle diameter, we assume the particles to be like spherical, right? But in case of fine grained particles, right, the particles which are less than 75 micron, none of the particle will ever remain to be this spherical, right? The particle will be flaky in nature, will be plate shaped, right? So can you assume this flaky particle to be a spherical? Obviously not, right? So that is one of the major kind of limitation of this particular approach, which we normally do in this hydrometer test, right? Next, what we assume is that the specific gravity of each of the particle are same, right? We don't say that the specific gravity of this bigger particle and the smaller particle are different. That we normally don't do, right? When we are supposed to get this percentage finer, we will be using one particular specific gravity, and that is a kind of an average specific gravity, which will not kind of give importance, or will not talk about the independence of the specific gravity related to each of the particles, right? So that is one again major kind of limitations of the Stokes law. Then in this Stokes law, what we are seeing is we are kind of allowing the particle to get settled down, right? But in Stokes laws are valid if if there is no restriction being imparted on the particle, right? Or in other words, the extent is infinite. So when the particles will settle in this measuring tube, obviously the particle will have different kind of motion, right? So particle will go and kind of touch or kind of get diverted because of this boundary, right? So that is something which is not to be there in the Stokes law, right? So this particular equation, or the percentage final equation which I was referring, right, those equations are valid only for the case if the particles are going to have a free flowing kind of environment, right? But here the particles will not be having that free flowing environment because of two reasons. Obviously, one reason that a particle will come and kind of get diverted because of this boundary, and obviously the particle will get kind of interacted or kind of influenced by each other, right? So one particle will have an influence on each other, right? So because of these two facts, there would not be any kind of this infinite extent which is supposed to be there in the Stokes law is not valid as such, right? So there will be obviously collision of particle, now particle interaction, but this can be kind of get reduced. What code suggests that if the soil suspension of 50 gram per liter or less is taken, then this is not a major issue as such, right? So we need not to be concerned about this fact, right? And while performing this test, we need to keep in mind that although I have said that below 75 micron, we will be performing this hydrometer test or pipette test, right? But we have to be careful that, let's say, if the particle is below 0.2 micron, then we can't do this particular test. Why? There will be Brownian motion, right? And even if the particle is greater than 0.2 millimeter, again we can't perform this test because there will be a turbulence, right? I told you about something called this velocity. While referring to this velocity, I've used the word terminal velocity, right? And if you remember, when I was talking about the terminal velocity, I've used the technical word laminar, right? I told that that velocity will be attained when the flow will be kind of, in a sense, laminar, right? May not be completely theoretical, free flowing this thing, but the turbulence should not be there, right? So these are some kind of restriction and some kind of limitations that are being associated with this law, and we have to be careful, right? That's what we mean. So now, eventually, from this grain size distribution, what we have seen, we have performed the sieve analysis, we have performed hydrometer analysis, and eventually we'll be getting a grain size distribution curve. We'll be plotting this grain size distribution curve. What you can see over here, that both actually are referring to the grain size distribution curve. Y-axis, as you can see, that it is from 0 to 100, right? But x-axis, it can be your x-axis can be kind of the maximum value can be plotted towards the left, or the minimum value can be plotted can be kind of placed towards the left, right? So that need to be you need to be careful, right? So grain size distribution curve, you can see it in this way also, you can see in this way also. But one thing you need to understand, that this graph should always be a semi-logarithmic graph, right? Why? Because the range of the diameter of the particles are huge, right? While having this soil mechanics in our undergraduate class, our faculty used to say this thing, that like the distribution of the particle can be assumed something like a football and the like the entire ground, right? So your particle can be of, in a sense, kind of the range of the distribution of particle can be within this football and the entire ground. So you can understand the difference of the particle size, right? So see here that it is 10 being written over here. I don't know whether it is visible. I have taken it from this internet. So anyway, the image probably not looking good. So this is 10 being written over here, and here it is written 0.201, right? So how many times it is higher, right? It's quite a huge amount of time, right? Now, if I would be plotting this value in arithmetic scale, I can't do it, right? So arithmetic, if I have to plot it in arithmetic scale, what I'll be doing is 10, 8, 7, 9, 8. So this thing I'll be continuing, and I'll be going up to that 0.001, means it will be quite a big line, right? So that's the reason we need to kind of use this logarithmic scale for the particle diameter to kind of enhance the smaller range and to kind of reduce this the bigger range, right? So see, the smaller range that actually get enhanced because of this usage of this logarithmic scale, and this bigger scale, right, or the bigger range actually kind of reduced by the usage of this logarithmic scale. So that's the advantage of using this logarithmic scale for this x-axis. But for y-axis, the value is from 0 to 100, and it can be plotted in this arithmetic scale. So here you have this arithmetic scale, you have this logarithmic scale over here. So this is a semi-logarithmic graph that is being used for plotting this this grain size distribution curve, right? So I'll be talking, or all my discussion will be based on the first way of plotting, right, where the bigger number is plotted in the left side, right? So in code, IS code, it is being suggested that what is the size of the particles or the name of each of the particle according to their size, right? So gravel is being, as I have already mentioned, that the particles which are higher than 4.75 mm, they are known to be gravel, right? And sand, which will be from 4.75 mm to 75 micron, right? And obviously there are far more classifications for each of these sizes, right? Now like this particular curve, right? So what this particular curve suggests us, that this particular curve suggests that that soil for which this graph is being obtained, that soil consists of all the particles. So gravel is there, sand is there, silt is there, clay is there. So when we'll be looking into grain size distribution curve, I'll be talking about that what are the things that we need to actually look into it, right? So we first need to see that whether all the particles are there or not, right? Then we need to see that which particles are kind of more dominating, right? Let's say for this case, what we can see, like for silt kind of material, right? How much percentage are there? So how much percentage finer is there? So it can be kind of read as like from maybe 65% to around 10%, right? So huge amount of silt seems to be over here, right? First of all the particles are there. That itself is a observation that makes sense. Next, that we need to understand that which type of particles are kind of predominating, right? So I will be showing you some more curve over here. Now, like, let's say if I talk about this blue curve, so yeah, so this blue curve, right? So it doesn't have any kind of this gravel, silt, clay, nothing is there for this blue curve, right? So the sand for which this blue curve is being obtained, right? So that that particular soil actually consists of only sand particles, right? Now you have one more curve over here, right? So this particular curve is some kind of different than this thing. So although we can see some the presence of this gravel, sand, silt, right, and to some extent a bit of clay, right, but one thing what we can see over here is there is this horizontal part, right? So what does that mean? This horizontal part means that there is missing of some particles. So here there's actually no particles as such. Now let's say if I will be just projecting this point on this x-axis and this point on this x-axis, what eventually I'll be saying is that the diameter for let's say this diameter may be, let's say 0.2 or 0.3, right? Oh sorry, this is high, so 0.009 or something like that. So for 0.009, if you have like 25%, for one also you'll be almost having 25%, right? So there is a missing of particles, right? So missing of particles or having a particle of uniform this thing shaped, right? Both the things are kind of can be treated as kind of not a good kind of linkage with the engineering properties, right? So now you can see one more curve over here, right? This kind of curve. What this curve actually replicate. Now the black one is a kind of typical grain size distribution curve. How this black line looks like? It looks like some kind of S shape, right? So S-shaped curve is something more kind of attractive, or kind of it gives a kind of implication that that particular soil is good in engineering behavior. But when you will have this kind of curve, right, which is some kind of convex upward, it tells a huge amount of different story, right? Obviously this kind of behavior will be viewed only for those kind of fine material. You will never see this red kind of curve over somewhere here, right? So red kind of curve will never be over here. Red kind of curve can be viewed mostly for this fine grained material. Why? Because fine grained material doesn't being influenced only by this physical stuff. The chemical stuff and the micromechanical aspect are very complex in this fine grained material, right? So when we talk about this, or when we see this kind of curve, obviously something should be there in our mind, that this material is highly not recommendable, right? There will be kind of collapse behavior. There is some kind of what should I use those? So there will be those behavior which is kind of unexpected, and which is kind of not to be kind of as long as this kind of curve is there, we have to avoid that particular material, right? So this is what this grain size distribution curve will fundamentally say about that particular soil, right? So let's say when I talk about this black line, right, what we can see is that this particles and these particles are kind of missing for this black particle, this thing, right? So it's in a sense, although it looked like a S-shaped curve, right? It is in a sense S-shaped curve, but whether it is recommended, to some extent, yes, if you don't have that this representation of all other particles, right? But this is also kind of a curve which talk about uniformity, right? All the particles will be kind of uniform in nature, right? So you may have this uniform kind of curve, right, where all the particles are uniform in nature, or you can have this kind of curve where all there will be some kind of missing particles, right? So you have this horizontal line, and horizontal line represents that missing stuff, right? Or you will have this red kind of curve, right? And red kind of curve is highly not recommendable, right? We will talk about that collapse behavior, right? So all these line actually represent the poorly graded soil, right? So none of this in a sense is kind of recommendable. So that is something we need to be kind of concerned about, that how the property of the soil need to be improved. So eventually we have a curve which will look like S-shaped, and at the same time there will be representation of all the this gravel, sand, silt and clay. All representation should be there in that particular curve, right? So as I was mentioning, well graded, when we see a well-graded curve, what it represents, that all the this particle sizes are being present, right? So from the small to bigger, all the size, all these particle sizes are being present. When I say this horizontal line, this horizontal line, which represents the gap graded part. Gap graded means there's something which is missing. So this particles, this particular size particles are missing, right? And when I say uniformly graded, right? So like this particular stuff, right? This black line, wherein we can see that the kind of dominance of one particular shape particle. Like here, what we can see, this particular shape particle, right? All these particular sized particles are kind of dominating, right? So this is being present in quite a huge proportion. So that is being termed as uniformly graded, right? So how to understand that from this grain size distribution curve, that whether we have achieved this our objectivity or not? We have to get these two parameters. One is known to be coefficient of uniformity and the other known to be coefficient of curvature, right? So coefficient of uniformity bears this particular relation. What is being said is we have to get this D60 value and D10 value. What is the meaning of this D60? D60 means that 60% of the particles are finer than this particular diameter. Now this D represents the diameter of the 60% finer, right? So let me repeat this statement again. D60 means that 60% of the soil are finer. You can see that here these particles are bigger, right, which is 40%, and here these particles are smaller in size in comparison to this particles, right? So D60 is a particular diameter, right? So what it represents, that below this particle, right, below this size, you have 60% of particle. So this 60% is kind of consist of this type of particle, right? And this particle, this 40% particles are making this amount of soil, right? So such will be the definition of D10 again. So D10, what do you mean again? The same thing, that 10% of the soil, right? Obviously the less amount of soil, 10% of the soil are less than this particular diameter, right? So that is the meaning of this D10, right? So from this grain size distribution curve, we have to get the value of this D60, we have to get the value of D10, we need to kind of plug it over here to get the value of Cu, right? Now, just you can think of it that if I say like D60 by D10 is equal to 1, what does that mean, right? So as this definition suggests, if we have understand the definition, D60 means that 60% are kind of finer than this particular diameter, and D10 means 10% of the soil particles are finer than this particular diameter, right? So if I say that D60 by D10 is equal to 1, so what I'm eventually saying, that so all the particles are actually kind of below this D10, right? So that is something. So obviously this shows that so eventually, if I will be drawing like this, so in your grain size distribution curve, actually this grain size distribution curve will be something like this, right? D60 by D10 is 1, right? So this will be like 60%, this is like 10% final. You will have this vertical line. So obviously this you can understand that the Cu value, actually why it should be higher, and it gives some kind of recommendation is given in the code that for gravel your Cu should be greater than 4 to term that gravel to be well graded, and for sand Cu should be greater than 6 for terming that to be this thing well graded, right? Now you can see this thing, that in this particular curve, this is a curve wherein we can understand that this is kind of obviously a poorly graded soil, right? A lot of particles are missing over this region, right? Now if I see the D60 value, D60 means 60% is here, I need to get the diameter. How will I get the diameter? I will just project it over here on this horizontal scale, and I'll have the diameter, and this diameter is something with this value 1.28, and for D10 the value is something this 0.2017, right? What is the value now? Greater than 6, right? So the question is, according to this definition, the Cu is greater than 6. So according to this definition, it seems to be well graded, right? Does it well graded? Obviously not, because 2 slides back I have said that this kind of curve will represent poorly graded soil, right? So But so can I use only this definition? So the what code suggests that no, this definition alone can't solve the purpose. You need to have one more definition, and that definition is this coefficient of this curvature, right? So you have to have this both this definition into account. If you use only this definition, you can have a misnomer, misrepresentation, right? So Cu seems to be higher than 6. So according to this definition, it seems that the soil is well graded, right? But and this is here you can see that most of the representation is for sand, right? And for sand it is being said that it has to be greater than 6. So what is the way out? We have to get this Cc value, which is known to be coefficient of curvature. And for getting this coefficient of curvature, we need one more diameter, and that is D30, right? We have already got this D10 and D60, and top of it, we have to get one more diameter to get this value of Cc. And finally, the code suggests that to say gravel to be well graded, we have to have this particular expression as well as this expression, right? So coefficient of uniformity and coefficient of curvature both need to be computed from the this particular the curve, right? Then we can say that whether a soil is well graded or not, right? So when we will be classifying the soil, so if the soil is more than 50% of coarse grain being present in a particular soil, that will be termed as coarse grained, and if it is less than 50%, it will be termed as fine grained, right? So yeah, this is like your now 50%. How will we get understanding it? That just by seeing the grain size distribution curve. So you have this grain size distribution curve. What we need to see is 50%. You will be for 50%. You will be drawing this line, right? And you will see that whether it is above 0.075, whether it is above this 75 micron, or it is less than 75 micron. Like for this particular curve, it is above 75 micron, right? So this is kind of coarse grained soil. Now, if I say this like this thing, fine grained soil, I'll be again plotting this curve, and I'll see that whether it is below or above this 75 micron. It is below 75 micron, right? So this is fine grained soil, right? So sandy soil, where all the representation is from sand, and these are the nomenclature being suggested, right? So, and here you can see that there are some kind of missing particles, right? So obviously for this silty clay soil, you don't have sand and gravel in this particular soil, right? Okay, so this is all about your this grain size distribution curve, right? So grain size distribution curve, as I was mentioning, this is one of the index property to talk about that or to give you some reference to the engineering behavior of the soil, right? Now this particular curve is being plotted for the entire soil, right? But consistency of soil is being kind of need to be find out exclusively for fine grained soil, because as I was mentioning, fine grained soil is much more peculiar. The behavior of fine grained soil is much more complicated than your coarse grained soil, right? So fine grained soil have more aspect into it, right? So consistency gives you some kind of representation of the fine grained soil. What it talks about the firmness of the soil, right? The soil can be soft, it can be medium soil, it can be hard soil, right? Now consistency limit, you have this liquid state, plastic state, semi-solid state, and solid state as being described by Atterbach. Remember this Atterbach, this entire experiment was around 1920s, right? And he was an agricultural engineer, right? And he have kind of he had given this definition of this consistency based on this only based on the variation of water content, right? Now when he was mentioning about this consistency, obviously some kind of assumptions are being taken over here, which I'll be mentioning, right? Now what he told, actually he told that the soil can be of any of this physical state. It can be in liquid state, it can be of plastic state, semi-solid state, or solid state, right? What is the meaning of that? Liquid state means that there is no shearing resistance of the soil, so soil will kind of flow like liquid, right? Plastic state, soil will have resistance, right? To will have shear resistance. It will not flow like liquid, right? It can be molded to any shape without rupture, right? So there is some kind of plasticity that is being attributed in this plastic state, right? when the soil will attain to this semi-solid state, what does that mean? Soil will lose its entire plasticity. It will become brittle, right? You can, if we mold, the sample will kind of crack, right? So there will be kind of generation of crack if the soil is semi-solid. And solid state means there will not be any volume change when water content is reducing, right? So what the experiment that he has performed is, he actually has started from this particular layer, right? So he has given a huge amount of water to the soil, and then what he was doing is he was kind of removing the water, right? So removing water means so water content will be now decreasing, right? So he was just trying to see that when water content is decreasing, what is the impact on the soil behavior, right? So while he was doing this experiment, what he has seen that there is a particular kind of demarcation limit at which the entire behavior of soil kind of changes, right? And those points or those water content limit are kind of very specific in soil mechanics, right? One of the limit is this liquid limit, right? Which says that this is the limit at which soil start to regain its shear strength, right? So if the soil is at this state, the soil doesn't have any shear strength. But the moment soil move, or at this state, this soil start to have some kind of shearing strength, right? Infinitesimal, but has some kind of shearing strength. And soil will have this plasticity behavior, right? Now, obviously, I'm not going to mention about the plasticity, but it will have this plasticity behavior again up to a certain limit. And that particular limit is being termed as plastic limit, right? And beyond this plastic limit, the soil will lose its entire plasticity. It will become like, it will behave like, it will have this brittle behavior. There will be crack generation, right? If we do a stress strain analysis for this liquid state, or for this plastic state, or for this solid state, we will never get crack on the soil. The crack will be there only if the soil is at the semi-solid state, right? And based on, he has given this liquid limit, plastic limit, and shrinkage limit, which in a sense are kind of one of the fundamental indicator of the fine-grained soil, right? So as I was mentioning, as your water content will be reducing, there will be the kind of implication in your volume change, right? So there is a certain zone up to which the soil will be in liquid state. Then there is certain zone at which soil will be in plastic state, right? What we can see is that be it liquid state, be it in plastic state, or be it in semi-solid state, one thing is common, that when the water content is reducing, volume will also be reducing, right? But in solid state, and that's how the definition of solid state, the solid state is a state at which there is no further change in volume. So volume will remain to be constant no matter how you change your water content. Why? Obviously, because of our mechanics which you haven't studied, the mechanics is unsaturated soil mechanics. So up to this portion, the soil is actually saturated, right? And beyond this, the soil is unsaturated, right? So we need to understand this thing. I have mentioned this thing, that up to this portion, up to this semi-solid state, the soil is completely saturated. Beyond it, the soil is not saturated, right? So there is, in this curve, this commonality, whatever the state is, this commonality is because of that saturation phenomenon, right? So the moment the soil start to behave like this unsaturated, the entire game plan actually changes, right? So then we'll have this solid state again. Now this liquid limit and plastic limit eventually will give us a number, and that number is very important in case of our design, and that is this plasticity index. It talks about the kind of range at which this plastic state is there, right? What it talks about, that what is the kind of probability of the particle to attract water, right? Higher the plastic state, it means higher amount of water will be there in the soil, right? If plastic state is lower, that means the amount of water that will be retained in the soil, that will also be lower, right? So let me just give you some the thing. Based on this plasticity index, we can say that whether a soil is less plastic, medium plastic, or highly plastic. When I say a soil is less plastic, what does that mean? It means that number of clay particles, these brown shaped particles are the clay particles, and these blue particles are the water molecules, right? Now, I have mentioned it a couple of times that all these clay particles are charged particles, right? So being a charged particle, it will attract water. So water molecules will get kind of attracted towards it, right? So less plastic soil means amount of clay mineral in that particular soil will be less, right? So less amount of water will be there. So when, if you get a value of plasticity index like 7 or something or below that, right, you need to understand that the clay mineral in that soil is less, right? So this is some kind of indication of this plasticity index. If if I say that it's a very high plastic clay, right, high plastic clay means number of clay minerals are very, very high. So the amount of water or the ability of attracting the water in that particular soil is also very high. So we need to understand this thing. So water, amount of water that will be kind of being attracted in that soil before attaining that liquid state will be quite high for this highly plastic soil, right? What it means, let me just make you to understand from this real field scenario. Let's say you have two soil, right? So you have this two soil. One soil is having plasticity index of 3 and the other soil is having a plasticity index of 23, right? What does that mean? So if you are kind of giving water to it, right, so less amount of water is required. So less amount of water will be required for this material to flow like liquid, right? If you are going to add water in it, so less amount of water will be required to make this the soil to flow like a liquid, right? And for this soil, you need quite huge amount of water. Why? Because this range is very, very high, right? Now this range is very high. You have a very high range, right? So that's how you can argue, sir, why this? Why are you kind of pushing this limit over here? You can push this limit over here also. Yeah, we can do this thing. But the point is that the amount of water that will be being stored inside the soil will be quite higher, right? Okay, so now if liquid limit and plastic limit are very close to each other, let's say liquid limit and plastic limit are almost same, what does that reflect? It reflects there is no clay mineral in the soil, right? So just by seeing this number, I'm just kind of giving you the impression of the relevance of this number. So just by seeing this number, that liquid limit number and plastic limit number, you can kind of understand this whether how much clay minerals are being present, right? So now you can ask, you can have this question: is it a possible case that with that plastic limit is higher than liquid limit? I will say that it may be. In some cases, it may be, but it's an absurd case, right? In most of the real field scenario, it will not be the case, right? Now, liquid limit and plastic limit, it can maybe a case that you can't determine liquid limit and plastic limit. So in those scenario, you have one more kind of value in this plasticity index. I have started this description of plasticity by only having this three stuff, right? Less than 7 and the other two, right? Now I'm adding one more stuff over here that it may be even 0. So for all these three case, right? If there are no clay mineral, it means your plasticity index will be 0. If plastic limit is higher than liquid limit, right? Which may be there may be a possibility, right? I'm not ruling it out. So again, so it will be a non-plastic soil, and there may be one more case where liquid limit and plastic limit is undetermined, right? Now, how to get this liquid limit value from the experiment? We normally use Casagrande and or cone penetration method, but in most of the cases, most of the labs people use this Casagrande method. And how it is being performed is just you need to sieve the soil, and whatever the soil that is kind of passed through 425 micron, that need to be collected, need to be put in this Casagrande apparatus. And so what need to be done is, before you have to have this soil of 120 gram, you have to mix this distilled water, preparing a uniform paste. Then you have to put it on this Casagrande apparatus, right? And now this is a ram that is being attached with it. You need to kind of revolve this ram, right? So there is certain kind of
गया उसका मतलब वो जान रहा है बंगाली की सलाह हमको पनिशमेंट मिला है.
Vikash Kumar ji, please mute your microphone. Yeah, Dr. Manash, you can continue.
Yeah. So so you need to place this soil paste on the Casagrande apparatus, and then there need to be this by using some kind of grooving tools. A groove need to be kind of created over here. So normally there are two different kind of grooving tools: this Casagrande tool or it is ASTM tool. Normally people use this Casagrande tool. So when we have this Casagrande tool, there is this groove being created over here, right? Can have this as this ASTM tool. Again, different type of groove will be created, right? Now, once this grooves are being created, we need to revolve this RAM, and there the revolution speed is being specified, right? And what we need to see that what is the number of this revolution which is required, so that there this in the bottom this low there is a continuity in the soil, right? So that need to be kind of viewed, right? That what is the number of revolution that is required, so that the continuity which is kind of removed because of that grooving, right? That is by kind of established after that disturbance, right? Now, while you do this test, you need to be focused about two stuff. That flow of soil is this is the correct way, but if there is any kind of slippage of soil, this is not acceptable. So when we rotate this this device, we have to be careful that there should not be any kind of slippage of soil, right? If there is a slippage of soil, you can understand it that this you can see this top surface will no longer remain to be horizontal, right? So there will be some kind of inclination. So this is not permissible. So there should be this flow of soil, right? And that need to be recorded. That two things need to be actually seen, that we need to record the number of blows that is required to close this groove, and after this groove is being closed, we need to take the soil from here, right? This soil need to be oven dried, and we have to get this water content of the soil, right? So two values are required, right? Number of blow count and the water content. Why? Because according to the definition that or according to the codal provision, that liquid limit is that particular water content which is being attained, or at which soil grooves closes in 25 number of blows, right? So for if you give this 25 number of blows, right? So the soil which will kind of or that groove which will close at 25 number of blows, right? So for that particular soil, whatever be the water content, that water content represents the liquid limit of that particular soil, right? So we'll have different, we'll do it for 2 or 3 tests. So, and eventually we'll be getting a linear slope, right? Now we need to be focused about two things. One is that number of blows. Again, these are being kind of placed in logarithmic scale, right? Again, we are using a semi-logarithmic graph, right? That is one stuff. And to draw a line, only 2 points are required, right? So even if we have just 2 points, we could have drawn a line, right? So you can take one more point just for the sake of this confidence, right? And you can have this line. And once this line is being drawn, we have to see that what is the value of the liquid limit at 25 number of water content. And that particular value will be regarded as liquid limit, right? And remember this thing, this liquid number is limit is a whole number. Let's say for this water content, probably you have got like 30.8 or something like that, right? So obviously the nearest whole number will not never report this liquid limit in any fractional value. Liquid limit has to be reported in whole number. And this definition is, or this stuff is valid for the plastic limit as well. Right, now there are two soil 1 and soil 2. Liquid limit of both the soil are different, right? Although the slope is same, but liquid limit are different. Now we need to understand what does that mean. So what is the implication of it? It implicates that your like in that particular curve, right? You remember this thing that we was talking about, this this plasticity index, right? So wherein I was talking about this liquid limit. So the meaning of liquid limit. So what does that mean for this particular soil? So soil 1. So soil 1 will lose its shear strength at quite higher water content, right? So you have two soil 1 and soil 2. You are adding water on it, right? Soil, both the soil will lose it this shearing strength, right? but soil 1 will lose its shearing strength at quite higher water content value. That is the kind of implication that you can understand from this particular curve, right? Okay, now based on this liquid limit, and I have not kind of skipped about this plastic limit determination. Now, plastic limit determination doesn't require this this sophisticated instrumentation as such, right? We need to roll it the plastic the soil, right? And as the definition suggests, that plastic limit this plastic limit is a situation wherein the soil will lose its entire plasticity, right? So there would not be any plasticity beyond this plastic limit, right? So if this is plastic limit, the soil will lose its entire plasticity, and there will be crack that will start to develop beyond it, right? So we will be rolling the this soils, right, into thread, and there is some kind of diameter being specified, and we'll see that at that particular diameter, that when the crack will start to develop, right? And that is the indicator of the plastic limit. So by the entire definition, this plastic limit will be kind of derived through this experimental process. So there is no kind of sophisticated equipment that being required for this plastic limit determination. Now, once this liquid limit and plastic limit is being determined, we can get the or we can kind of classify the soil, right? So we have this plasticity chart, which is in a sense the sacrosanct for fine-grained soil, right? What does this plasticity chart gives us? It is a chart between this plasticity index and liquid limit, wherein we are seeing one important line, this A line, right? So above A line, if a combination of plasticity index and liquid limit gives a place to your soil above the A line, that means that soil is clayey soil, and if it is below this A line, though that soil is silty soil or organic soil, right? As you can see that above A line, you have this capital C, right? That actually indicates clayey soil. And below this A line, you have either this M or O, right? M indicates silts and O indicate organic soil, right? Now we can see two more this vertical lines, right? So at 35% liquid limit, we have one vertical line, and at 50% liquid limit, we have one more vertical line. So this two vertical line actually demarcate the region into three segments based on the compressibility. So this particular segment talks about low compressibility. This segment talks about high compressibility, and the soil which actually remains in between these two vertical lines, they will experience some kind of intermediate compressibility, right? So this particular this plasticity chart based on this A line gives us the information whether the soil is clayey soil or silty soil, and what is the compressibility that need to be attributed to that particular soil, right? And that's how we kind of classify our soil, right? So soil, you have this coarse-grained soil and fine-grained soil. As I was mentioning, if like 50% is retained by that 4.75 mm, right? So it will be like this coarse-grained soil, and if it is 50% is being passed through that 4.75 mm, then that is fine-grained soil, right? So in case of coarse-grained soil, we have this gravel and sand, right? And now gravel and sand, they are again being classified, right? And I'll show you that this classification type. So what we see is that in gravel, we can understand that whether a soil is gravel or sand, how to identify it? We have that demarcator. The demarcator is that 4.75 mm, right? So if 50% of that particular soil is above 4.75 mm, that means gravel particles are predominating, right? So that's a gravelly soil, right? Now in that gravelly soil, we will see that what is the fine content, right? If the fine content is less than 5%, we need not to do any kind of consistency test. If the fine content is within this 5 and 12%, we need to check a bit in this plasticity part, right? And if it is above 5%, obviously we need to come to that plasticity chart, right? So if it is less than 5%, we need not to worry about anything regarding plasticity, right? If the fine content is less than 5%, we will just look into our grain size distribution curve, get the value of Cu and Cc, and both based on these two values, we'll be saying whether it is well graded or poorly graded, right? if the fine content is more than this 12%, right? Actually, it should be 12%. So if it is more than 12%, we are supposed to have perform this plasticity analysis, and we need to see that whether the soil is below a line or above a line, and whether it and what is the compressibility of the soil, right? So what we need to see is that we have one to name a soil, we need two kind of symbols, right? For gravelly symbols, obviously G symbol is there, right? Now we need to understand that our soil, this gravelly soil consists of more than 12% of fine particles, right? So either the fines will be clay or it will be silty, right? So if it is clay, then C will be attributed with that G, and if it is silty, M should be attributed, right? So that we need to see over here. That's it, right? Whether it is C or it's M, right? And for if you need any further classification, then we will be seeing that whether it is high compressibility or low compressibility. But mostly for the gravelly soil or for the sandy soil, these things are not required unless the project is kind of quite important in nature, right? Now, if it is like if the fine content is within 5 to 12%, right? Then we need to attribute dual parameter like this thing. This is well graded soil, and along with well graded, we need to mention that whether that gravel contains silt or whether it contains clay, right? So a similar thing that can be associated with the poorly graded case, right? So for gravel, for the sand, again the same stuff. We need to see that how much fine content is there with the sand, right? Is it below 5%? Is it within 5 to 12%, or is it above 12%, right? So we will use the nomenclature again in the same way. The only difference is in the first case, the first symbol was G, and here the symbol is S, right? Now, if it is silt or clay, then along with that a line, right, we have to see the this two vertical line as well, right? The 35% line and the 50% line, to understand whether it is low compressible or intermediate compressible, or is it like high compressible, right? And that's how we'll be performing this grain size distribution curve and this consistency limit, right? Liquid limit, plastic limit, right? Although I haven't talked about shrinkage limit, because shrinkage limit actually is not required for this classification stuff, right? But shrinkage limit is far more important, especially for special kind of soils, right? Now, based on liquid limit, plastic limit, and grain size distribution curve, what we have understood is how we will be identifying or kind of naming the soil, right? So we have understood that how the soil need to be named based on these three tests, right? Okay. So this is the test that we have performed just to talk about. So for the test that we have performed, that actually talks about the qualitative behavior of soil, right? So be it this grain size distribution test or this consistency test, they actually talk about, in a sense, qualitatively how the soil will behave, right? Now we'll be seeing two tests for understanding the engineering behavior of soil. One is the compaction test and the other one is severe test, right? I'll slowly go into it because I have spent much time on the qualitative this part, right? Compaction part, which actually talks about the engineering behavior of the soil directly, right? It actually gives you some kind of indication that what will be the your shear strength of the soil if you can understand the compactive behavior of soil, right? So let me just make you to understand from this diagram. So let's say we probably all have seen this this basic soil phase diagram. We have the solid, water, and air phase, right? So in case of compaction, we applied some amount of energy from the external sources, right? Now, when we applied that that energy, right? So this air portion will be reducing in size, right? So here, there will be a case where there will not be there will not be any kind of air being present over the soil, right? So what actually is happening? Soil particles are coming closer to each other, right? So when the soil particles will be coming closer to each other, obviously there will be densification, right? Now that is actually our objective, that how to improve the densification of soil, because we can understand one thing very clearly, that higher the densification, higher will be the shearing strength, higher will be the stiffness, right? So the densification is some kind of, it's a kind of an indicator of the engineering behavior, right? So to densify the soil, one approach is obviously compacting the soil, right? So through this compaction, we are actually removing this here portion, and the soil particles are coming closer to each other, right? So the air, so let's say these are the soil particles where air is being trapped, so air is kind of removed from the portion, and eventually soil particles are coming kind of closer to each other, right? Now this is a kind of indicator of this densification and higher amount of shearing strength, right? Now what we do in soil mechanics lab, we to understand that how the soil will behave in the field due to this external agency, we perform this something called this Proctor test. So there are these two tests, standard Proctor test and modified Proctor test. So both the tests eventually that's actually the same thing. The only difference is that in case of modified Proctor test, we kind of apply higher amount of energy in compared to the standard Proctor test, right? So let's say in case of let's say standard Proctor test, if you have like 3 number of layers, here we kind of compact the soil in 5 number of layers, right? So in case of standard Proctor test, if the height of fall, as it is being written in FPS unit, it's 12 inch. So in case of modified Proctor test, it is like 18 inch, right? So if the fall of height is higher, obviously the impart energy will also be higher, right? And the weight of this rammer is also kind of quite high in case of the modified Proctor test, right? So what I will say in the next slide, I will just mention about that this compaction curve, right? And which is actually the sacrosanct of this compactive behavior, right? What we can see over here is this, there is a curve that is actually obtained from the laboratory, and this curve is between dry density and moisture content, right, or the water content, right? Remember this thing, this is dry density part, so we have to, every time we have to get the dry density for each of this water content, right? What we can see over here is that as we give as we add on this water, right, dry density is actually increasing up to a certain part, right? And beyond that it start decreasing, right? So the question will be there, that why is that so? Now in the soil mechanics book, there are two kind of in a sense hypothesis that is being proposed, but there is no kind of what should I say, no experimental kind of observation being made, right? So only the hypotheses are being proposed, that why this behavior is something like that. And what they say is that when yours, like when water content is less, right, the soil particles, there is something called lubrication theory. So what it says is that the particles can be in a state of in a state of that case where the particle can lubricate on each other, right? It can roll on each other, it can slide on each other, right? So as you go on and on adding the water, right, so the particles this lubrication effect will go higher and higher up to a certain particular water content. And beyond this water content, actually what happens is that water start to come within this particle, right? What I'm trying to say is that let's say some amount of water is being absorbed within this at the surface of the particle, right? So when there is this adsorbed water, so there is two different kind of water, we can assume it in that way. One water which is like free flowing water, right? The water which is not being adsorbed by any kind of particle, right? That water can be flowing freely. That is one kind of water. The other water which is actually being kind of attached to the surface of the particles, right? So if the water are kind of attached to the surface of the particle, as I was showing in that while I was mentioning about the plasticity index, right? So these clay particles look something like this. They have negatively charged, right? They are negatively charged, right? They will be attracting water. So let's say when the water is being attracted, so these water particles are kind of attached to this particle, right? So this will give this lubricating effect, right? So when you are kind of adding more water to it, so more number of water particles will be kind of will be added to this surface, right? If more number of water particles are being added to the surface, higher will be the lubricacy. And if there is higher lubricacy, the particles will come closer to each other, right? And once the particles start come closer to each other, the density will be increasing, right? But this effect, this will be there up to a certain moisture content, right? Beyond that, what moisture content, that the water particle will not get attracted to this surface, right? It will behave like a free flowing, right? And once it start to flow like freely, so the particles will be driven away from each other. The particle will be driven from away from each other, and your dry density will be reducing, right? That is in a sense one particular theorem to explain this particular curve. There is one more theorem that is based on double diffuse layer. I'm not going to it, but anyway, so I suppose this theorem is much more kind of easy to understand. So because of that particular phenomenon, you have this inverted V-shaped kind of curve, right? This is very important, especially in transportation engineering, right? So in case of transportation engineering, we need to figure it out that what is the water content at which we are going to have the maximum dry density, right? So this maximum dry density talks about a lot of stuff, right? This is a kind of a condition which people want to have, right? Now in some case, obviously there are some projects where you need to have the soil which is at this side, which is known to be dry side, and or this side which is known to be wet side of optimum, right? That's based on the project itself, right? So but anyway, so what this laboratory test is showing us, this laboratory test is giving us this particular implication key, what is the amount of water needed to be added while we perform this compaction, right, to have the maximum density, or to have the our kind of targeted density, right? You can have different targeted density, right? Now, as I was mentioning, that in soil mechanics lab we perform either standard compaction or this modified compaction, or which is known to be modified Proctor test, wherein we give higher compactive effort. So if you give higher compactive effort, the change will be on this peak point. The peak point will be shifting, right? So shift of peak point means what? Shift of peak points, and on this right hand side, what does that mean? It means that your along with that increment in your dry density, there is also a change in the water content, right? So you need less amount of water to be added on the soil, right? So with less amount of water, you will be having higher amount of dry density, right? So as your compactive energy increases, your kind of this compaction curve will be shifting towards this side, right? So that is one thing that we need to understand, that how we are compacting the soil. We can compact the soil by different method, as I have shown over here, right? This rammer, vibratory plates, smooth rollers, rubber tires, and all this equipment in the field will impart different amount of energy, right? We need to understand that higher the amount of energy, your this compaction curve will be on the right hand side, or will be shifted towards the right hand side, right? So that is one implication of this compaction energy. But apart from the compaction energy, there are many more influencing factors that actually governs the compaction behavior, right? So but compaction energy seems to be one of the major important factor for this compaction curve. What it says, that increasing compaction energy means lower moisture content and higher dry density, right? That's one of the stuff that need to be understood. Now, apart from this particular test, wherein we can understand that how the dry density and water content need to be kind of achieved in a particular project, right? From our laboratory test, there is one more laboratory test that we often perform in test in the laboratories, and that is California bearing ratio test. Now, what does this bearing ratio test give to us? It talks about that what is the kind of penetration that will be there, or in a sense it talks about the deformational aspect, right? As I was mentioning about this compaction talks in a sense about the strength aspect, right? This California bearing ratio talks about in a sense your deformational aspect, right? So I'll straight away go to this definition. So what did this definition give to us? That it is the ratio, which is obviously expressed in percentage, of force per unit area that is required to penetrate a soil mass with a standard circular plunger of 50 millimeter diameter at the range of 1.25 millimeter per minute to that required for corresponding penetration in a standard material. So let me just make you to understand this statement. So CVR, how will we be getting the CVR value? We have a plunger, right? We have the standard stuff, right? What we need to see is that how much load is required. So end of the day, our objective is to see that how much load is required for that plunger to have a certain amount of penetration, right? And that certain amount of penetration is being specified at either like 2.5 mm or 5 mm, right? That's again based on the different aspect, right? So there is a rate at which you will be kind of applying the energy. So this rate is being specified as like 1.25 mm per minute. So based on that rate, we'll be plotting something called load versus settlement curve. So this is this load versus settlement curve. Let's say this is your load versus settlement curve. What is the objective? So we need to see that where or how much load is required to have that 2.5 mm penetration, right? So let's say this is your 2.5 mm penetration. So corresponding to this 2.5 mm penetration, what is the load that is required, right? So this is what we need to plug over this in this equation, right, to get the CVR value, right? Now there is some kind of codal provision to it, that CVR of 8 to 9% that is kind of recommended, right? Now that's how you will be actually getting the some kind of influence of the deformational aspect of the soil, right? So that's from my side. So to summarize the entire stuff what we have read over here, I started with the qualitative the response or the qualitative behavior, how we kind of tap it in the laboratory, then some kind of quantification, right? Quantification of the mechanical strength and stiffness both, right, in the laboratory that is required directly to be used in the transportation engineering or to the subgrade soil, right? So these are the four stuff in a nutshell that we have discussed over here. Yeah, so that's it from my side. Thank you.